Welcome to the jungle gym, where there is an engineering feat. No, not this feat, this feat. The swing set can be broken into two components, the frame and the swing. We start with the swing. It forms a pendulum. At rest, the pendulum is in a state called equilibrium. But when displaced, it will move back and forth about this equilibrium position. The further away the swing moves from equilibrium, it begins to slow down, and as it returns, it moves faster. This is the swing's velocity. At maximum displacement, the velocity is 0 meters per second. A pendulum has two main forces acting on it. Gravitational force. This force acts down towards the ground, and tensional force. This acts along the chains of the swing towards the pivot point. At the equilibrium position, these forces act directly opposite to each other. But in motion, they begin to act at an angle, theta, relative to the swing's rest position. To determine the forces acting on the seat, we are required to resolve these forces. Firstly, we seek to determine the swing force. The force acts in the same direction of the motion path of the swing. Force of the swing and gravitational force form a right angle triangle. Note the angle of the pendulum relative to the rest position is the same angle opposite to the swing force. Using the trigonometric identity, sine theta is equal to opposite over hypotenuse. We relate this to the triangle and get sine theta is equal to the force of the swing, F of S, over the gravitational force, Fg, which when rearranged gives Fs is equal to Fg sine theta. At this point, it's important to recall Newton's second law of motion. Force F is equal to mass m by acceleration a. We apply this to F of g. Therefore, we now have Fg is equal to mass by acceleration. Finally, when applied to the swing force equation, we get Fs is equal to mass by acceleration by sine theta. The next force we seek is the tensional force. As previously stated, this is the force along the swing exchange. Its angle is the same as previously used. The trigonometric identity we use, however, is cos theta is equal to adjacent over hypotenuse. Following the same format, we get Ft is equal to mass by acceleration by cos theta.
To begin, we must assume a point of origin. In this case, we assume it to be the point at which the swing set is at rest. That is, the point at which velocity, acceleration, and displacement all equal to 0. All these quantities are vector quantities, and so have both magnitude and direction. For example, if the swing set is pushed forward and it gains a displacement of x, then when it comes back to the origin, it would have a displacement of negative x, as it travels in the opposite direction. And so its total displacement would be 0, while the distance traveled, as it is a scalar quantity, which only considers magnitude, means that the distance would be 2x. Therefore, the sign, whether positive or negative, would indicate the direction of the particle. When a force is applied, such as pushing the swing, it gains velocity through acceleration as time passes. Hence the equation of motion formula, v is equal to u plus at, where v is the final velocity, u is the initial velocity, a is the acceleration, and t is time. Due to the swing being connected by chain to another fixed point, the swing acts like a pendulum. Therefore, the swing curves upwards. This motion is known as curvilinear motion. This motion can be broken up into horizontal and vertical motion. The horizontal motion would have an acceleration ax of 0, and so the velocity would simply be the initial horizontal velocity. To find the distance traveled in the horizontal plane, one can just use the formula x is equal to x0 plus uxt, where x is the final displacement, x0 is the initial displacement, ux is the initial horizontal velocity, and t is time. The vertical motion would have an acceleration due to gravity acting downwards, and so the acceleration would be equal to negative gravity. That is, negative 9.81 meters per second squared. The velocity can be seen to have a formula Vy is equal to Uy plus Ayt, and the displacement y can also be calculated using the equation of motion formula y is equal to y0 plus Uyt plus a half Ayt squared, where y is the displacement, u0 is the initial displacement, uy is the initial velocity vertically, ay is the acceleration due to gravity, and t is time. At the highest point the swing reaches in its motion would indicate that it's reached the peak of its oscillation due to the force applied. At this point, velocity is 0, while the swing would still have an acceleration of negative g. A formula for projectile motion can be obtained from the equations above. As we assume the origin as the point of rest of the swing, the initial displacement in both the horizontal and vertical plane is 0. Therefore, we can get an equation for t as t is equal to x over ux. And now, substituting that into the formula for y, we get y is equal to uy on ux by x plus a half ay by x squared on ux.
In structural analysis, the forces in the members of a truss are asked to be determined, and this can be done using either method of joints or method of sections. The forces acting on the members of frames and machines composed of pin-connected members are also analyzed. Now, using hypothetical measurements of the swing, the forces in different members can be found. The side view of the swing is set up in a way that it forms a truss. A truss is composed of slender two-force members joined together at their endpoints. Now, the assumptions made about this truss is that the members acting at the point is connected by smooth pins, and also the load is applied at the joint. And the third assumption is the members have negligible weights. With these assumptions, the forces through members AC and CB can also be calculated. For instance, if someone were to sit on the swing, they will exert a force at joint. This force will be in tension on the joint the person's weight acts downwards. Hypothetically, the person has a mass of 50 kilograms, and the following calculations can be done by assuming the acceleration due to gravity, g, is 9.81 meters per second squared. From the free body diagram, since there are no horizontal forces, AX now the first step would have to be to calculate global equilibrium. And to do this, we find the reaction forces. The first reaction force, AY, is calculated using moments about point B. Now, assuming the moments about point B is equal to 0, AY is calculated to be 245.25 newtons. After doing this, the sum of the forces F in the y-axis is equal to 0. By can be calculated, and it is found to be the exact same value as AY, which is 245.25 newtons. Using method of joints at joint A, the angle it makes with FAC is equal to 67.38 degrees. The sum of the forces in the y-axis again is equal to 0. This is such that FAC sine 67.38 plus AY is equal to 0. FAC can be calculated now to be minus 265.69 newtons. This is equal to 265.69 newtons in compression. Since a negative value was obtained, this means that FAC is in compression. Also, FBC is calculated to be 265.69 newtons in compression, since the truss is symmetrical.
The preceding concepts and subsequent calculations are neither completed nor clearly communicated to your intended audience without including their respective units of measurement. A unit of measurement is a definite magnitude of a quantity that is used as the standard for measurement of the same quantity. The Bureau International des Poids de Mesure defines the system of international units, abbreviated SI. The BIPM's mission is to ensure and promote the global comparability of measurement. The CARICOM, which Trinidad and Tobago is a state, is one of the 41 associate states that subscribes to the BIPM's outline. SI units are the units for measuring base quantities, which are time, length, mass, electric current, thermodynamic temperature, amount of substance, and luminous intensity. The corresponding SI units are the second, meter, kilogram, ampere, Kelvin, mole, and candela. All these units are quoted to be independently dimensionless. Derived units are a combination of base units as a result of their algebraic relations. The names and symbols of these units can be replaced by special names and symbols, which they themselves can be used to form more expressions and symbols of other derived units. An important example of an SI derived unit is highlighted throughout this video. That is the Newton. The Newton is the SI unit of force. Algebraically, force is the product of a body's mass, which has an SI unit of kilogram, and its acceleration. Acceleration considers the measurements of base quantities, length and time, and has base units of meters and seconds. The algebraic expression of these base units results in the units of acceleration to be meters per second squared. Then, the SI unit of force is kilogram meter per second squared. This combination is expressed as the derived unit, the Newton. Just to recap, the 7 SI base quantities are the second, the meter, the kilogram, the ampere, the Kelvin, the mole, and the candela. And the unit of force is a derived unit, which is the Newton. And if clearly communicating and calculating the relationship of your considered base quantities and its derivative to ensure global understanding of your mathematical expression of your ideas is not enough motivation to always include your SI units, your professor will deduct marks if you do not include them in any submitted material.
In conclusion, I hope you learned something today. We learned force vectors,
Kinematics.
Structural analysis.
Units of measurement.
The more you know.